All right, well, good afternoon, good morning, good evening. Welcome everyone to today's webinar on AI-powered simulation. We'll be taking a look into physics AI with an Altair. My name's Drew Buchanan. I am the engineering manager here at True Insight. We are the North American reseller and channel partner for Altair products. So if you ever talk to me, I probably may have talked to you in support. I'll be leading today's webinar, but as I kind of kick off a few of the intro slides, I'm just going to start a poll and feel free to, you know, answer those questions as you see fit. Just gives us a better idea of, your familiarity with AI solutions and simulation solutions. So, great. One of the things, if you're unfamiliar with Altair, we are a simulation company with a number of simulation tools. And today we're going to be delving into how to utilize physics AI, which is integrated across the portfolio, but specifically we'll be looking at it within the context of structural simulation. Keep in mind, we have a number of other solutions, within data analysis, design modeling, and with the recent acquisition of Siemens for Altair, this portfolio is going to be expanding. And as probably a lot of you know, AI is really kind of expanding across, the engineering space. You're going to see a lot more of it. And I'm excited to kind of be talking through today what physics AI can do and how it can really help you specifically with your own types of simulations and scenarios. Yeah, again, if you're unfamiliar with Altair, we are embraced globally with the recent acquisition of Siemens and Altair. I mean, we have pretty much customers in every single space that are utilizing this technology and also utilizing physics AI. So if you're a current Altair customer, uh, you may have already been exposed to it, or you may even have access to it. And after this webinar, feel free to kind of delve and jump into it. My colleague is in the support chat right now. So if you have any questions as I'm going through the webinar, feel free to answer those questions, send questions via the chat. He will be able to address them. If not, I will look at them at the end of today's webinar. So let's take a look at the agenda. We'll first kind of delve into what is physics AI and where does it fit in the Altair space. Then we will take a look at an example on a Three Rivers bike rack. I'll talk about that in a moment, but we'll be breaking down how to actually work through a workflow in physics AI, which would be training models, testing models, and then predicting new models. And like I said, we'll close it off with questions, but if you have questions as we're working through the scenario, feel free to send them in the chat accordingly. All right, so let's delve into what physics AI is. So physics AI within the Altair space is a geometric deep learning engine. Really, it's designed to kind of aid analysts and designers to make fast predictive models in CAE simulation. Uh, you know, one of the cool things about it is we can utilize it for simulation, but also CAD-driven data. And it actually has capabilities for machine learning for both structured and unstructured data. So, if some of you used, HyperStudy or some other tools, it really allows you. It's a little bit more sophisticated in the fact that it allows you to look at a bunch of data sets or models and actually predict and generate an algorithm to kind of look for solutions in the context of what we're looking at today would be displacement and stress results. Like I kind of already mentioned, like traditional methods, like what you might see in HyperStudy, it's working off of morphing and consistent meshes. Physics AI doesn't need to have those capabilities. It really allows you to kind of build off of those kind of more basic kind of regression-based models. So, in one of the really before we jump into this, why would this be useful for you? So most of you are in this webinar, I imagine, are analysts or stress analysts or CFD analysts. You are going to be using simulation. You're probably going to have numerous data sets, product sets that you've utilized. As you know, pre-processing or meshing or setting up the model can take time, but then even solving the model can take time. And even in the context of this model, which is a linear static analysis, you'll see this is kind of the timing for the exact model we're going to be working through in this webinar. In a traditional FEM on one model, on solving on a 12 core, which would be a traditional engineering laptop machine, it takes about 5 minutes and 30 seconds to solve this problem. When we look at physics AI, it's 5 seconds. And you can see the order of magnitude, 2.17 e to the 7 Pascal versus 2.14 on the predictive model for the same exact geometry. Kind of see the stress distribution exactly kind of identical. It's really going to speed up your time. So for those of you who are, you know, in the simulation space and working off of designs, this really can be a game changer in kind of getting solutions much quicker. Thank you all who have participated in this poll. I'm just going to close out the poll here, and let's keep working our way through this. So how does the workflow work? Specifically, the workflow within PhysicsAI is and I'll step you through this process, is we first create a project, and then we generate or load our data sets. Specifically, the data we're going to be using machine learning to train and then also to test. And I'll delve into this a little bit more as we go through this. And then after successful testing, which is, after PhysicsAI generates a working model, you actually test it and make sure it aligns with actual accuracy. From there, you can actually take this PhysicsAI model and predict on brand new models. So that's the general workflow to begin. We will kind of work our way through this as we kind of set up our models. So our data set is we're actually going to be working off of this Three Rivers bike rack. I went to University of Pittsburgh. I lived in Pittsburgh for a number of years, and I'm an avid cyclist, so I thought this would be a fun data set to look at. So if you're unfamiliar with Pittsburgh, city in Western Pennsylvania has three rivers, and you see this bike rack actually kind of utilizes that design where it has the three rivers of Pittsburgh set up in the scenario. What we'll do is we'll actually utilize Inspire. And Inspire actually has a recent release feature where you can actually work off of images and generate a design. I'll show that real quickly. But also one of the cool things about Inspire is you can actually utilize this for DOE to actually generate a number of data sets that are parameterized. And then we'll kind of take a look at PhysicsAI and look at prediction models for stress and displacement. Keep in mind, you don't have to use Inspire. You can utilize SimLab to write a script for automation for large data sets. You may be working with a product where you might already have 30 different designs that are kind of similar. But I'm kind of starting from scratch with this model and generating a data set that we can use in PhysicsAI for prediction. The idea being, I think there's a couple hundred of these bike racks in the city of Pittsburgh. Big thing is reducing cost, but also making sure it's very structurally capable. It's a city that's very cold, lots of extreme weather conditions. We want to make sure that it lasts for that capital investment while kind of minimizing cost. So a very common thing for the engineer or designer kind of executing this with looking at different designs, running simulation, making sure it meets the stress and displacement allowables. And you can imagine already trying to run multiple designs, it eats up a significant amount of time. And so PhysicsAI is a very capable model for this. All right, so let's first build our data set. I won't spend a ton of time here, but there's some cool things we can do in Inspire to work our way through in terms of setting this up. So let's take a look. I'm going to jump into Inspire. So for those of you who are unaware what Inspire is one of our simulation-facing tools. It utilizes our structural solver, specifically our implicit solver OptiStruct. There's also a solver in it called SimSolid, but for this case, I use the OptiStruct solver. But one of the cool things about this is I started from scratch in terms of I grabbed an image. These bike racks have been around for a good bit of time, but I actually kind of reverse engineered the design. So let's take a look at how I went through that, and I'll step you through how I actually generated the DOE. And we'll go through this relatively quickly, but just so you're aware of how this was set up. So first thing we can do is one of the things with Inspire, like I said, this is a recent feature, a few versions back, is we can actually import an image plane specifically, which I grabbed an image of the bike rack right here, and then I actually generated the design accordingly. Cool thing about these image planes is you can scale them to be what the true design is which that's what I did. I set the scale so to make sure it was kind of an accurate assessment of what the bike rack would actually look like. After I actually did that, I went through the process of setting up the problem itself. Remember, this is a structural problem. Bikes are sitting on it statically as they're locked to it, so we can assume it's a static loaded case. And the materials themselves are, just basic steel, something that can be easily manufactured. So perfect application of a linear static analysis and something that can be used in Inspire. So, I am restraining on the bottom feet right here, the types of loads and structures you have. If you're curious about it, we've run a number of webinars in the past on Inspire. I'm not going to spend too much, but we can pretty much run everything you'd expect in a capable structural solver within Inspire. Note, you could do everything I'm showing right here. This is just building up the data set. You could do it in SimLab or HyperMesh, and you have capabilities for nonlinear analysis as well for PhysicsAI. I'm doing it within the linear, a linear static analysis. So there's a force here and then a force on this face. So if I go click there, you kind of see where the bike would be leaning up against the bike rack. And about 100 pounds, you could probably go higher or lower. That's, assuming there's two bikes on each of these racks, which is kind of a typical case. And a lot of bikes now are, in that 20 to 30 pound range. So one of the cool things we could do in terms of the setup is obviously we can kind of solve this for one case, but I used Inspire in a unique case using the Design Explorer to generate a large number of data sets, specifically about 55 different data sets. And I did that through parameterizing the geometry. Specifically, what I did is if I go to the extrusion depth right here, is I created a variable of saying 2 inches would be the extrusion depth. And then I ran a DOE, which is kind of a set of experiments where I kind of vary that dimension accordingly. This is known as parameterizing our data set. It's very easily done in HyperMesh or SimLab, but I'm doing it in Inspire. And it's cool, you can actually set variables in Inspire, makes it very kind of user accessible to do this. So I go there and I go to my actual Design Explorer. And one of the things I can actually look at within the actual setup here is I have a number of design variables here where I'm varying that extrusion depth between 1.6 to 2.4. And I can actually set it as discrete values, or I can set it as a continuous variable. Discrete variable being I actually am telling it, what I want each of the variables to be, versus continuous, I set the number of iterations, and then Inspire kind of sets that extrusion depth. And then what I actually get when I actually finish the analysis in this DOE is I have, a number of different scenarios with different, up to 50 different scenarios. And, I actually have this data set actually generated accordingly. The cool thing about it as well, within, if you're just curious when you're running DOE, I can actually look at results specifically if I want. If I can actually hit load all results and actually look at it within the Inspire context. So kind of a good thing to keep in mind when you're going to be using data set. How does the stress and displacement look? You can animate displacement. Hey, this makes sense. And I actually have my setup. So this is kind of our first first process is we're actually building out a data set to train our PhysicsAI model on. What PhysicsAI is going to utilize is it's going to utilize these results files specifically to actually kind of, train and kind of build out a predictive model accordingly. All right, so that's our kind of our first step. And then our next process here would be when we jump into HyperMesh is we actually need to start our project and actually load these data sets. So let's show that now. So a couple things, if you don't have the PhysicsAI banner showing, PhysicsAI has been around in a number of releases. It's not by default showing in HyperMesh. You just have to go to View, Ribbons, and then turn on PhysicsAI. Kind of cool thing about this, it's a left to right kind of workflow. Some of you might be legacy HyperMesh users, so this is in the new interface. One of the things in the new interface, a lot of it's from like a left to right kind of design flow, much like how Inspire is set up or even SimLab is set up. making it a little bit easier. So it's kind of the same thing in PhysicsAI as we kind of, we'll work our way from left to right until we actually, build up our prediction of our model. So our first step is we want to actually generate a project. So this is where we save our project file so we can reload it. You'll see I'm actually going to be using a kind of a loaded project because it took some time to solve the actual PhysicsAI training, but we will set it up and then we'll actually kind of look at finished results. So we can name this as, whatever you want to name it, and then you can actually specify the location where you wish to save it. So I'll just name this as webinar, and then I'll put this project file in this folder. All right, so kind of straightforward to begin. That's our first step, and that actually kind of sets our project accordingly. Our next step, what we can do is we actually need to actually set our data sets. So our data sets are going to be our training model and then our testing model. I'll talk about the testing model in a moment. The testing model is pretty much how it actually kind of tests the PhysicsAI machine learning model after it generates to make sure it's accurate. So you'll have a data set for training and a data set for testing. Typically, you're going to have up to about 50 data sets for training. You can have a little bit less, but you typically want to have a little bit more. And then testing is usually about 20% of that, depending on what you have. All right, so let's hop back to my slide deck here, and we'll talk about what training is. All right, so our training, this is really what where we actually train our system and what we're training it on. In the structural context, we are going to be, training it in the context of displacement and element stresses, which would be our von Mises stresses. So that's what you'll see me work my way through. And you'll see we can, kind of control it via a number of parameters that are specific to machine learning, models. So WIP is really controlling the size of the PhysicsAI machine learning models, how many different patterns it can kind of look for. Depth kind of controls the complexity of the patterns and how far information propagates in the local area. So these are settings which you'll actually tweak depending on the scenario. There's a number of kind of default settings that we suggest in terms of setting up the model, and you can kind of adjust accordingly. One of the things that's usually the better kind of technique, and we'll talk about the idea of overfitting and underfitting in a slide, is really if you don't have a great PhysicsAI training model, meaning after you train the system and you start looking at accuracy, you can kind of adjust some of these parameters right here, but really the better kind of solution is to kind of have look at your data sets you're utilizing. Are you using too little data? Are you using too much data? And kind of adjusting the actual training data sets accordingly. Like I said, you can train on less than 50 data sets. Sometimes they might work totally fine, and other times you may need to increase the number of data sets. A couple other things in here to kind of point out is your epochs. This is how many iterations, and this is really how it's kind of going through and kind of building up this machine learning model, how it's going to be trained. How the more epochs you have, the longer it takes to solve. The nice thing on PhysicsAI, it is something that's utilized on both CPU, GPU in terms of solving. And this is going to be kind of one of the things that kind of influences how long this specifically solves. The final thing is the types of methods of machine learning. So there's the GCNS method, which is the graph context neural simulator. This is kind of the most kind of stable one typically during training. And it's really kind of more optimized on CPU. TNS, which was introduced in 2025, is the transformer neural simulator. A little bit better to be more efficient than GCNS on GPUs. And this one's also mesh size invariant, so it can really help in terms of smoothing if, depending on your mesh data, maybe it's a little bit coarse, this can sometimes help. And then released in the latest version, which is .1, which was released earlier this summer, is the shape encoding regressor method, SER. which really works on vector outputs. In our case, we're working on field data specifically. So we're going to be kind of sticking to the GCNS. I did try a case on TNS, but kind of similar in terms of application. And there's a substantial help on this. I am not a computer scientist. I'm a Mechie by trade, but these are kind of really nice neural networks that can be set up specifically for training accordingly. One of the big things, though, that will be important in terms of everyone that's using PhysicsAI is how accurate your training model is. And this is something that I think every engineer can relate to specifically, is the types of data sets you're going to utilize. So in our case, we have, we're going to be looking at these bike racks, and we have a data model what's going to vary the extrusion for 50 different data sets. If we started having too many variables or too many different things changing, you might have an application where the model's not generic enough. You might have something known as overfitting in the application. And then another thing like underfitting, you might not have enough data actually in the system. So overfitting and underfitting are things you don't typically want. The training loss curve, this is what's actually being computed by PhysicsAI, and the validation loss curve, these are curves that are generated from your existing data sets. So an optimally fitted data set will actually be very similar. You kind of see that best fit approach, and you'll see that in the model I actually utilized in PhysicsAI. So kind of think about it like this: is if you're trying to kind of create a regression curve, and some of you probably have done some regression analysis in the past. If you have too many variables, it can really kind of affect the design space, and if you have too little data, that can also affect your prediction model. So with that being said, let's jump into actually looking at training within the system. All right, so we'll jump back into HyperMesh here. So I'll kind of show you we'll actually show you how we actually load these models specifically, and then I'll actually show you the model I worked off of. So the first thing we need to do is we need to load the data sets for training. So if I go here and create data set, kind of a nice specific system here. I'll talk about a couple things that are nice that are built into the PhysicsAI framework. In a moment, this extract solid faces feature, but we can name this as what we see. I can name it as webinar training, and then we can actually grab the model. So we're going to be specifically training off of our H3D kind of systems. And what we can do is we can grab this folder. By default, you're going to see it's going to grab every single H3D file. So again, like, you don't have to use a DOE or automation. If you're a company that already has a lot of variance in your designs, you've been working as an analyst, and like I've tested 30 different cases where maybe I'm tweaking some small geometry changes, etc. You might already have these existing H3D files, and H3D is just a compressed results file that's native to Altair, specifically Hyperview. What I would do is I can extract these all over. So this is going to be the 50 data sets I utilized for training. So if I go over here, bring them over, I can actually grab everything I'm specifically after. And then I can actually hit OK, and that's going to actually go through it. One of the cool things about it, there's this feature called extract solid faces, which actually, if you're using mesh data that is all solid mesh data, it'll actually extract the solid faces and just do it kind of in a shell context. And you can uncheck this. It'll actually take longer to solve, but this is a way of kind of efficiently going through the system. So there's different tools and techniques we can utilize to make this even more efficient in terms of predictive modeling. So if I hit OK, what it's going to do, it's going to go through this process of extracting data, which will take a few moments, depending on what the data sets are. It may be a quicker amount of time or a longer amount of time, but for the context of this model, we're going to look at a kind of a finished kind of setup here. So if I actually go to my data sets now, you'll see what happens in terms of large data. It'll actually show you everything that's within the system. And so in this case, I'm kind of just interested in the displacement values and then also the element stresses. So I can actually see in my data that this data set I've generated, how good the data looks specifically in regards to displacement, and then also stress, whatever you're going to be training your model on. And what's highlighted in orange are small outliers. You can choose to include this data or choose to exclude this data. So again, really shows you how effective your data sets are in terms of going through this. And there's even some cool features specifically on actually displaying the existing H3D files if you wish to utilize that. That's another kind of cool feature. You also see in here in kind of my finished working file, I have my testing file as well. So again, you'll load, and I'll talk about that in a moment when we actually bring up testing. You'll have a separate testing data set that is completely different than your training data set that you're working off of. So let me go back to here. Still working its way through extraction. And what you'll actually do specifically on the model training end is you can actually, after you actually extract the data set accordingly, is you can actually train and set up the model. So if I hit the plus symbol, this will be where you can actually specify the training. You'll see the data sets automatically recognized by PhysicsAI. So this is the data set where we extracted, and you can specify, what you want the name of the training to be. So I can say this is training webinar. And then what I actually want to train off of. So I'm going to go off of displacement and stresses. And here's where we can kind of specify what we, kind of known as hyperparameters of the PhysicsAI model, which we can kind of adjust accordingly. Again, we can kind of work off of our default settings. One of the nice things that we have is when we actually start to test the model, we can test our effectiveness. So, if you're going to start messing around with PhysicsAI after this webinar, one of the things I suggest is kind of reducing the epochs a little bit, just to kind of start and make sure you have kind of a good training model that's set up. So when you actually go through training, what will happen is it generates what we talked about, a loss curve, which shows you how well the data is fitted. And so this is the model I prepped, our bike rack, which is cool. It's actually showing us, hey, this is a good fit model. And so what we have as we were kind of going our way through is you kind of have a couple peaks in the beginning. And I ran this, I think a little over, around like 900 plus epochs, and it finishes, like around like 890, where it's actually our final model. It's going to show you a star. And what you'll kind of see is what you want to have in terms of an optimally fit data specifically is your validation loss, which is your existing data sets, and the training loss, which is the PhysicsAI model that it's building, should align when it finishes. This is going to tell you, hey, you have a pretty good training model to begin. Now, if you're training on multiple things, in our case, we're training on displacement and stress. This training loss value, which if I go to the log value right here, it's going to show you just what this value is in regards to stress and displacement, what it is. And then it's going to tell us, yeah, so it's actually 882 was the best loss, meaning how similar it is to the validation in terms of how it builds out this actual predictive model it's going to utilize. Great. So with our model actually set, and I'm just going to come back here, so it's still working its way through that, is we can actually jump into talking about testing. So what actually has been done in terms of the training, it's building up the actual predictive model it's going to utilize. So in our case, it's generating a predictive model, so I don't actually have to run an actual structural analysis. I'm not going to solve those system of equations and go through the stiffness calculations, et cetera. It's going to use that predictive model and go through it. But one of the things we need to do is after we train and build up that predictive model is we need to test it. And so one of the key things with PhysicsAI is we actually have a testing procedure we can utilize. The testing procedure means you'll probably, in the case of the bike rack, I'll have a couple of other models specifically I wish to utilize in terms of testing it. Typically, a good procedure should be, between 10 to 20% of the model should be reserved for testing. In the case of this model, I think there was 50 data sets I worked through, and I think I tested on 5 or 6 different models. And what happens, those 5 or 6 are actually solved finite element models with, like I said, PhysicsAI can be utilized for a number of things. Doesn't have to be structural analysis, but in the context of what we're talking about, it's structural analysis. So I have 5 models I've run in traditional FEM, and I actually am going to test the PhysicsAI model. And so what it will actually do is it will actually look off of the predictive PhysicsAI model and compare it to the tested model. And it will actually do that through something known as a mean absolute error. So it'll look at the displacement and the stress and how far apart the predictive model, the PhysicsAI model, is to the actual solved or tested scenario. That's why it's really important, the testing, when you're going about this process on your own, is the testing models should always be exclusive or unique from the training model. You should not be using training models for the testing model. And additionally, if you're kind of a data science geek or you're a computer scientist, there's other metrics we can test, like MSE and RMSE, so root mean square error, and there's a number of other applications we can talk about. So let's look at actual testing. So similar to this, I think it's still going through that data extraction. Let's go look at our testing. So one of the things, like I mentioned, is you'll actually have another data set right here for testing. Very similar, you would just want to make sure if I go to hit add data set, you would go to the folder and I'd go to my testing folder. And we would specify this folder, and you'll see these are unique data sets that haven't been part of the training. Again, we're looking at trends on stress and displacement, so we're using the H3D file. And so once we do that, we can bring those in accordingly. So let's take a look at our existing testing data. So the testing settings are very straightforward. It's just, hey, here is our model that we're testing off of, which would be the training model we've already trained. And then we can specify, once you finish this training process, we then specify testing. And then once we click on testing, you'll see when it finishes the scenario, it'll actually give you these MAE values, so these mean difference of errors. But really the cool thing about it, is I can actually display the difference between the real value and then the actual predicted value. So if I hit display file, and remember, this is the predicted value is the PhysicsAI, the predictive model that we're generating, that's being generated in the background. And then the real value is an actual run FEM model. And you'll see it within the same hyperview context. And we can actually see when we're looking at displacement right here, how does that displacement align accordingly, which is pretty cool. I can go to a different model here, hit display file, and I can actually kind of have really good confidence. I can look at these numbers and see that the error is reasonably low with all of these, 1 to 2% error. And remember, it's factoring in the units, for stress, displacement, et cetera. That's what we're seeing, these kind of scientific notation accordingly with it. But you'll see right here the displacement populating, which is also kind of cool. So predicted, this is the PhysicsAI model. True would be kind of the resulting H3 or already run FEM model. So that's going to be our step. The other thing that you can, like I already mentioned, if you want something that's even more substantial than looking at the MAE, you can actually go to the detailed report. And then there's a number of other kind of statistical measures for both displacement and element stresses. So again, just giving you confidence that your predictive model is an accurate model that you've kind of generated. And pretty cool. You have these values available at your disposal. Most engineers and myself, since I've started utilizing this, is I'm going to use MAE, which is the mean absolute error. But you kind of see all these are broken down. you know, in terms of what they are, MSE, mean squared error, etc. All right, so let's go back to our slide deck and then we'll talk about prediction in a moment, but let's jump back to our slide deck here. All right, so one of the things that, you know, typically after we kind of, you know, test our model and make sure that MAE value is relatively small, is we can jump to our PhysicsAI prediction model. So predictions can be done on both mesh and CAD files. In the context of our case is I'm gonna just load another bike rack with a different extrusion depth and meshed. So I'm gonna have a different FEM file I'm gonna load. I'm gonna do that in hypermesh. And then, you know, then we're actually gonna go run through and predict that model specifically. And you'll see how quick it does. We'll do it in real time. So typical, you know, kinds of rules of thumb, typically predictions tend to be better for mesh files as opposed to CAD files, but you can do predictive on CAD models if you want to. A couple things, again, I already mentioned this in the beginning of this webinar, specifically is kind of to help the prediction typically is having more data. You could have very easily run this model for less data sets. You know, one of the things, you know, you'll see in that validation loss graph, which I showed earlier, you can only really have that graph if you have 50 pieces of data, but you could run it with substantially less. You could only have 20, you know, 20 pieces of data, but you're not necessarily certain how accurate that those values are going to be. And you're only going to know that if you start looking at your MAE value during testing, how well it corresponds with it. But like I mentioned, one of the easiest ways to kind of improve your PhysicsAI model is just to have additional data sets, or you can kind of tweak your training settings. You know, the training settings are what it's actually doing to actually build that predictive model. So, you know, one of the things you can do is you can kind of adjust the epochs in terms of having more epochs accordingly. You'll see in the help specifically, if you have a lot of noise in your data, maybe jumping up to maybe like 3,000 epochs, et cetera. These things can kind of adjust and help you in that regard. And then, yeah, like making sure you're checking the MAE value. I talked about that, and checking your testing data. How does it correspond? Will kind of help you in terms of your actual prediction of your model accordingly. All right, so let's jump to a demonstration of the prediction. And we will do that now. All right, so now that our model has actually been tested, so like we kind of talked about earlier, hey, the testing's been done, the MAE values all look good for both stress and displacement. I feel pretty good about this. What I can specifically do then is actually run a prediction. But you'll notice in my main screen, I don't actually have a mesh. I need to import an FEM file. So I need to do that first. So I can go to File, I can go to Import. I'm gonna grab a solver deck, and I'm gonna grab that, just an FEM file here. So FEM being OptiStruct solver deck format. Again, you can use PhysicsAI with a number of solvers, et cetera. I'm just doing it within the OptiStruct context. All right, so this is a model here with a slightly thinner diameter that's outside of our data set, and we're going to actually predict it. So now that I'm ready, I can just hit the predict option right here. Oh, I need to set my model. So let me go back. So yeah, one of the other things you can actually have multiple different PhysicsAI models, which is pretty cool. You could have, you could have like 5 or 6 different models, and so one of the things I have to do is I just have to set this as, hey, this is the model I want to use to predict my data. Since I only have one here, I just need to set active model, and you'll see this option for releasing model. This would be if you have, a couple different, predictive models you wish to test. You can do that accordingly. So it's going to set this model, and then we can actually go through that and use it to actually predict our system. All right. So now that it's set, I can close this, and then if I hit predict, you'll see that in the lower left-hand corner, it's telling you, but like it went through that entire process. Like I've timed it out in like 5 seconds. So you see that it's finished. The actual model is now done. What it's doing, it's actually loading in the window automatically for you, the hyperview file. So pretty cool about this is you'll be saying, well, Drew, hey, we trained on stress and displacement. You're only seeing displacement. Well, it actually loads a hyperview window, which I can maximize here. So I'm going to do that. I'm going to make it a little bit larger. There we go. And, you know, if you've ever used Hyperview before, Hyperview is our dedicated post processor. This is what we, I've run a couple webinars in the past on Hyperview. Feel free to check them out, but you can actually go through and post process on this predictive model. So if I turn off displacement, I can turn on stress and actually look at my stress values. And again, PhysicsAI works off von Mises stress. I can see, all right, I am within the design allowables right here for a smaller diameter. And I've saved a bunch of time in terms of not having to run an FEM, like 5 seconds. Again, just illustrating how useful this type of analysis can be and really help us get results a lot quicker. If you are in a very iterative design space accordingly. Great. Let me come back. I'm going to make this a little bit minimized. So let's do it again on a different model. Kind of cool. We can let's just try and predict it on a totally different model here. So I am going to clear this session. You'll see that the other thing is when a model is set within PhysicsAI, even though I'm clearing the session, this model is still set. You'll see right here, if I have a drop-down menu, if I want to change it, I can. But this is telling me, hey, I'm still working off of the large demo model. You can always open up an existing PhysicsAI project as well. So in the course of running this demo, I think I actually have a couple different models here. So if I wanted to go to here, you'll see here's this project I could open up and have. So you still have the ability, once you actually build these projects, these models in PhysicsAI, I can actually open them. But I've already set this model. So what I want to do is I want to import a new solver deck just so we can take a look at just another model with a different extrusion depth, how quick it can be predicted. All right, so let's import this solver deck. I'm going to open up a different one. Okay. Importing it accordingly. So slightly different depth for the model here. Make it a little bit larger, and then I hit predict. Since the model's already set, it's already finished. So again, like 5 seconds. So once it's actually finished, it's actually going to load the hyperview file for me automatically. All right, so slightly different displacement in this model. Still, again, very minimal in terms of the system, but let's take a look at our stress values. Very similar to the others. So again, kind of meeting the criteria that I'm after in terms of saying, hey, this is an acceptable limit. Great. So, that kind of brings us to the last 15 minutes, which I'm going to save for some questions. One of the things I would say is if you have some further interest, check out our blog and our YouTube for further information for PhysicsAI, but also some of the Altair products. One of the great things about Altair as a company is every product we support, there's training on it, and there's active training already for PhysicsAI, which is part of your license. So very easy to kind of integrate this accordingly. And one of the other things that's really nice about PhysicsAI specifically is there is a very nice kind of documentation, if you want to get in the weeds and the neural networks, already built into the interface. So with that being said, I am just going to turn it over to some active questions to kind of finish things out here. All right, so let's take a look at some of the questions here. Yeah, so some good questions. Yeah, so first question on transfer learning, you can actually transfer a model specifically that you've already built on PhysicsAI to a different model. Specifically, there are some caveats there, specifically of how different that model is, and that MAE score can be used accordingly. But you can, specifically do that. Yeah, and yeah, you can use specifically, nodes, et cetera, as input, and then stress and displacement as outputs. That's that first question. As far as the technical team, you know, uh, you can reach out to me. I'll put my information in the chat if you want to reach out to me specifically. Um, you know, uh, I'll put it in the chat if you want to reach out to me, and I can kind of go through some further technical questions for you. So here's my email in the chat. And I don't know specifically, if Mohammed, if you're a current existing customer of us at True Insight, but we are pretty agile. Myself or the other engineers on our team should be able to reach out to you pretty quickly. And most of the sales guys know to kind of put me in touch. Okay, sounds good. You can reach out to me. Happy to kind of let me put it in the chat. I'm sorry, I should send it to everyone. So let me put it in the chat. There you go. You should see it now. You should be able to have that, Mohammed. And kind of the other question here, is there a way to improve the existing AI model with new improved data sets? Yep, you can specifically do that. That's kind of a part of the process of transfer learning. You can actually do that with kind of improved data sets. So yeah, you can do that. Good question. So there's a couple more questions here. Sean, I'm taking a look at your question right now. So good question. And I can send you a little bit further information, Sean. I know you and I worked in the past together a little bit, but it's different than a traditional DOE. It doesn't have to be structured. The purpose of the physics AI model, it can work off of structured data, but also unstructured data. And so that's kind of the purpose of those validation loss settings in terms of setting up the training of the model. And you don't have to perturb data or morph the mesh. Generally, it works off of, you're kind of in the ballpark of what the geometry is going to be. If I was training a model in a bike rack and then I gave it an automotive chassis, it's probably not going to be an effective model, but you could test it if you wanted it to, but it's probably not going to behave efficiently. So yeah, specifically with traditional DOE, like probably what you're running currently is you always are going to be running that FEM simulation. What we actually ran in predictive physics AI, what you saw at the end, it was actually using that model and predicting it. So that's why it's able to obtain a solution in 5 minutes. So say you have a nonlinear analysis that takes you an hour or two to run, in traditional DOE for each scenario, and you have 50 scenarios, you're looking at, a couple hundred hours of run. And with physics AI, a predictive model, it's going to get it a lot quicker. So it's going to behave more efficiently and more effectively. If you have further questions on that, let me know. I think I answered that question. And good question there, Sean. I appreciate it. But did that answer your question generally? Okay. I'll shoot you. I think I have your email, Sean. I'll shoot you a little bit more further information if you're curious there. Happy to do it. Um, yeah, and then Dave, in terms of parameter values when training, we can kind of check or uncheck those accordingly, when we're actually going through training. I think there's a couple more questions, so just give me a second. But thank you for your questions. I will follow up you on that question. I'm pretty certain it can. Specifically, the question on fatigue life training. Pretty certain it can handle that. But I will just confirm that for you. But it should be able to handle it because the way fatigue life specifically works is you run a structural analysis and then you use a tool like ours called Hyperlife, where it then kind of looks at the alternating stress and then actually goes through it. So I think I'm pretty certain it's supported for PhysicsAI, but that's a good question. I'll follow up with you there accordingly. Any other questions? Anyone else? I appreciate all the questions uh, within within this webinar. And any final questions from anyone? Sounds good, Mohammed. Nice to meet you. Um, I'll stick around in the chat just for a few more minutes if anyone has any final questions. But if there's no final questions, thank you so much for attending. We will put this recording up on our YouTube page. I will paste that in the chat below just so you have it. Yeah, and definitely, I think it's pretty cool. I think what PhysicsAI can do, definitely if you have access to Altair tools, mess around with it. It's definitely really neat what it can do and take advantage of it. So I'm going to paste our YouTube in the chat where you'll find this webinar. Yeah, and I think that's it. I don't see any further questions in the chat here, so I'm going to wrap up this webinar. Hope everyone has a good rest of your day, and looking forward to chatting with you all in the future. Take care, everyone.